Welcome to a lesson with Dr. Powell. Let's take a look at trigonometric substitution in integration. So we start with an integral, and this integral might have part of a Pythagorean theorem. See how we have like x squared minus, and this is 2 squared. So awfully like what happens on a right triangle. If x would refer to the hypotenuse and 2 would refer to one of the legs, so hypotenuse and legs. Now, in general, if we have something like a squared minus b squared, a can represent the hypotenuse. If we have something like a squared plus b squared, both of these will represent legs. Okay, now here's for two common triangles that we can use when we're thinking about trigonometric substitution. One is just 1 cosine theta, sine theta, and theta. And the other one is obtained just by simply dividing all the sides of this triangle by cosine. Secant theta, tangent theta, and 1. So we look at our current triangle, our current setup from this, and we decide which of these models it fits in. In particular, we look at where the constant is. Where's the constant? If the constant is on one of the legs, we'll use this one. If the constant is on the hypotenuse, we use this one. In this particular case, since the constant is on one of the legs, we use this triangle setup. But we want this triangle to match this one. Now, in order for that, we have to multiply this 1 by something, so we get a 2. So we multiply all the sides by that to make so it's a similar triangle. So we multiply everything by 2 here in this triangle. 2 and 2. Okay. Then, and we won't be needing this triangle right here. All right. So, and then we have some equalities. X is equal to that, and 2 is just that. So we're done with this triangle because we've kind of married the two of them together. All right. So that's the triangle we're now looking at. And this one triangle is the triangle that'll help us with all our substitutions. Now, we actually engineered this triangle so that what the expression we had over here actually solves for the other side, this side right here, if we were to take a square root of what's circled here, which we do here in the formula. So that means that this is the square root of x squared minus 4. You can check that using the Pythagorean theorem. All right, and we have a dx, remember that. Okay, that's actually very important. All right, so that means that this integral can naturally turn into, look, this part right here we can substitute with just 2 tangent theta. And then dx, we need to be able to substitute that. Well, we use the idea that x is equal to 2 secant theta. And so if we were to take the derivative of x with respect to theta, we would get 2 secant theta tangent theta. And this allows us to write dx is 2 secant theta tangent theta d theta. So we can simply replace the dx with this, 2 secant theta tangent theta d theta. Notice how the tangent thetas cancel. And then we're left with, and those cancel, so we're just left with the integral secant theta, which in another video we know is natural log of absolute value of secant theta plus tangent theta plus c. And now we just have to rewrite this back in terms of x, which we can. Notice that secant theta, we can solve for it right here, is just x over 2. So this will be natural log of x over 2. And then tangent theta right here is, well, it's going to be, you just solve for it right here. So it's going to be square root x squared minus 4 all over 2. And that's the result. We just successfully used trigonometric substitution. Thanks for watching.